Talk about the course progress. I'm happy all of you already submitted your A1 to me. So give me a few days to 1 week, I will grade them. Your second assignment will be due 25th. So you still have probably less than 2 weeks, but you should have enough time to do that. So I don't have any upcoming deadline soon, so you guys should be fine. We are still in chapter 2. We will continue to talk about the calculations for solar position, and then today we are going to talk about more advanced system, online calculators, the sun position. Those ones are actually most interesting than the hand calculations. So we will cover that, and the last class will be sky luminous distribution model. This will be taught on Wednesday. Okay. Do you have any questions about the A1 or anything else? You're good? Okay. All right. Then let's start to talk about the slide. I actually made a few changes on the Canvas course website, a few updates, and let me tell you what I did. Basically, in chapter 2, you will have the chance to do the samples chart, which you haven't explored yet. But last year, the samples charts prepared by University of Oregon was kind of down. So I switched to the 2 alternative websites for you to use for the class last year to use. But right now, they worked out the solution. So the website is back. So I think we still need to use this one. Yeah, because this is the best. So I put a preferred here. So you want to know, yeah, you can use this one. You can still use this too, but to me, this is more like a professional. Yeah, I will show you later. Yeah. Right, so let's start to talk about the slide. That's a sample chat, but we won't talk right now. We will talk about some old stuff, calculations. Okay. So you already practiced how to do the solar time calculation. Solar time basically is the real time of the sun in your local site. It's not necessary to be the same as your clock, because your clock is for the entire time zone, and your entire time zone is like for a beat over there. So, for example, Kansas City versus Hayes, we are in the same time zone, but actually we are in different solar time because we are in different longitude. Makes sense to you? So the solar time is actually the real time for that location. And then we did some calculations to calculate the solar azimuth angle, altitude angle. You guys practice very well. The answers are very close. But I think it'll be enough, okay? Because we are going to use online calculators later, or my Excel calculators. And then let's talk about 2 more important angles. Solar azimuth angle, solar altitude angle, they are very important to know where is your sun, right? For example, the azimuth angle, let me test it. In the morning, should the azimuth angle, the results, calculated results, should it be negative or should it be positive? For morning time, when you use the source, it's reference. Negative? Yeah. So if your calculated results is a positive value for the morning time, that means something is wrong. Okay. The negative doesn't mean anything, it's just like telling on which side of the sun, actually, right? And in the afternoon, the calculated solar azimuth angle should be positive if you use the source as a reference. But if you use the north, there is no positive negative because the north should be from 0 to 360 degrees. So they all be positive, but you can always convert the angles for the source to the angles for the north because they're very easy. Right? And then solar altitude angles, this one should be positive all the time. Why? Because when you have the sun visible, that means it's above the horizon, then the altitude angle should be positive. If it's negative, it means it's below the horizon, then you should not be able to see it because it's below the horizon. If you do have the solar altitude angle negative values before the sunrise or after the sunset. That makes sense, right? So for this one, it has no reference south or north. It's always the same, right? Because this is just above the horizon, below the horizon. So that will be always positive. And then let's talk about the two more important angles, the incident angle and the path angle. Because the azimuth angle and altitude angle is actually telling you where is the sun, but it has nothing to do with your shading lines, right? I know where's my sun. How can I do my shading to block the sunlight when I don't need it? So we use all the two angles, which called the incident angle and the solar path angle, to do that kind of configuration. So if you are dealing with shading, you should use incident angle and path angle. If you are not dealing with shading, you just want to know where the sun, then you use azimuth angle and altitude. So that's difference. But they're actually related because the incident angle and solar path angle, they will be calculated from your altitude angle and azimuth. Okay, so that's the same. But let me explain to you what is the altitude angle and what is the let me see if he's here. Okay, he's not here yet. The altitude angle, I mean the incident angle is the angle between the incident sunlight and the normal to your window gradient, which is very similar to the incident angle we define in the 6th grade class of the electron. For example, when you have a light bulb, for example, this one, right? Although this is not on, but if I plug in, I'll have this light bulb on. So when you guys do the inverse square law calculation for the point measure, do you still remember? Hopefully, right? I'm still here, and you just took it last semester. So when you calculate the incident angle of the electron line for the point measure, the incident angle is defined as a light, the angle of the light come to your calculation point between that light directions and the normal of the tabletop, right? And this one is very similar. So the incident angle is the angle between the incident sunlight and the normal to your window gradient. Okay, in this case, this will be the angle right here, because this is the incident light, right? And this is your normal. So this angle should be the angle right. Let me see. AI, right? So should be this angle. Okay, because you have your sunlight coming in this point, and you have your normal to your window gradient is this way, right? So the incident angle should be the angle right here. Or if you use the other half to show it, it will be this way. Make sense? Or if you use the actual window here, right now I don't have visible sunlight on this side, but I do have visible sunlight on this side. So if I say I have my visible sunlight, you see, coming from the sun to this one, and then this angle should be the angle between my incoming sun ray or sunlight to the normal of the window gradient. So that would be 3 Make sense? Okay. So this angle is actually very easy to understand, and it's technically easy to find out. Okay. But the solar path angle is a bit complicated. The solar path angle actually have two angles. One is called the front path angle, and another one is called the side path angle. The solar path angle is defined like this one. The apparent altitude angle of the sun normal to the building face. Then for the building face, you have, when we say the building face, we mean the face of your window gradient, right? Because a building typically have multiple walls, at least 4 walls. We are talking about the wall or the building face with your window, you looking out, right? So in this case, say this is your window gradient. You have your sun right here outside. You are standing behind the window, inside, and then the front profile angle alpha P is defined as the projected. You see, this is your sunlight, right? So when you project your sunlight to this vertical plane perpendicular to your window, you say you got a projection right over there. So that angle, that projection line will be like this line. This is the sunlight. When you project the sunlight to your perpendicular plane of your window, you get a projected line right over there. Make sense? So the front profile angle is actually this angle between the projected sunlight and the normal to your window. So that's this one. It's a little bit different from your actual incident angle because your actual incident angle is right from here to this normal, but your projected front profile angle should be just a portion of it. Okay, that is a three-dimensional relationship. Make sense? You get it, right? Okay. And then the side profile angle is a bit different. In this way, the side profile angle is the projected sunlight not on the perpendicular plane, but on the window gradient directly. Between that projected line, let's say this line, and your window. Parallel on the gradient, so profile angle on the side is parallel on the gradient. So that one angle should be the projecting angle on your window, and the actual vertical angles to the zenith in this case. Okay. Why? Because this angle is trying to see how far away the sunlight is, the angular distance is from the center of your window gradient when you use the zenith structures to that sunlight direction. That's a side profile angle. So if you have these two profile angles, you can actually define where is the sunlight coming from and how could I do my shading device. So let's take a look at the shadow over there. If you look at that direction, you see we have a sun shadow over there by the overhang of the roof over there, right? So let me ask you, if you look at this line right here, you see that this line? Is this line the angle of the front profile angle or the side profile? So let's do the judgment by the definition. The front profile angle means the sunlight projected on the perpendicular surface, which is perpendicular to the window gradient. That's this wall, right? The profile, the projection of the sunlight on this wall and the normal direction. So this angle should be front profile, right? On your side profile angle is the other way. Side profile, you have your sunlight projection on your side wall, and then between the, let me actually show you another step to make it clear, because we cannot actually see this side profile angle in this way. So let me show you the other direction. So if you look at this, you see we have a window here, right? We have a shade. It's part of the roof over there. And this angle, because we are concerned about the forward directions, so this angle should be the front profile, right? And this angle should be the side profile. Make sense? Because the side profile angle is on the side, and the front profile angle is in front of the window. If you remember like that. So the side profile angle is always an angle on the wall itself, on the window itself, and the front profile angle is an angle perpendicular to the window. if this explanation is easy to understand, then you just use this one. Okay, all right. So let me go back to the actual calculation equations here. So for us to calculate the front profile angle and the side profile angle, we have to know the incident angle. So the incident angle alpha I, so the incident angle is an equation of RT cosine alpha T. T is the solar incident angle, okay? And then alpha Z is the difference between axis and building orientation angles. Maybe explain to what's the difference. So the axis angle, you guys remember that axis angle is the sun position projected on the ground and the angular distance to the true south. So in this case, this will be the alpha S, that's the axis angle. Make sense? And in this case, this is the west in the afternoon time. So the axis angle should be calculated as positive. So that's this angle. Right? And then you have a building orientation angle. This is your building. Of course, this is part of the grading, right? And you have your building behind. So this is your building orientation, and your building orientation is this angle. That's your alpha E, building orientation. Okay. So the difference between the axis angle and the building orientation angle is this angle. Make sense? Right? So in this equation, when you try to calculate the solar incident angle, you just need to know the solar altitude angle and the difference between the axis angle and the building orientation angle. That should be this angle. If you know these two angles, then you will be able to calculate the solar incident. But the front profile angle is calculated differently, right? It's calculated like this way. The front profile angle is arctangent sine alpha t. Alpha t is the solar altitude angle divided by cosine alpha I. That's your solar incident. If you have your solar incident angle calculated and you know your solar altitude angle, then you should be able to calculate the front profile. Yeah. And this one will be related to the building orientation because the building orientation has already been counted in your alpha Z calculation. Okay. And then you have another angle for the side profile angle. This one is arctangent your front profile angle divided by your tangent, your difference between the axis angle and the building orientation. Yeah. I put these angles here because the textbook did not have this equation, but you actually have this equation. So I just worked out and I put it here. Okay. So then you have all the equations to calculate, right? This is the way I figured out how can we do the side and the front profile angle. That's the original equations I used. So maybe look at this scenario one more time. So this is your window grazing, and you are standing behind a window in this room, and your son is in front of you, right? And then we are interested to know what will be my front profile angle and what will be my side profile angle. I need. Why I need that? Because if you know the front profile angle, if you know your side profile angle, you know exactly the size and the location of your shading. Make sense? For example, right now, since the shade is already designed and money over there, so your maximum front profile angle for that moment will be this angle. Make sense? And your maximum side profile angle will be this angle. That's the maximum. How about if you calculate the front profile angle is actually smaller than this angle, then what will happen? Say if your sun is coming this way, that's the maximum shading angle provided by the shade. But if you have calculated front profile angle is smaller, your sun is visible. The sunlight will come in, right? But if you have calculated solar front profile angle is larger, that means it will be blocked by your shade. Yeah, that's why we need to calculate the profile angle. And on the side profile angle, right now you have a maximum shading angle on the side, like this angle. So if you calculated side profile angle is smaller, that means you will have visible sunlight coming to your space, right? If it's larger, then the sunlight will be blocked by the shade. There won't be any sunlight coming into your house from the side. Make sense? So if you know the front profile angle, we know the side profile angle, then we know exactly how large your shade should be. Right? For example, if you calculated the side profile angle is smaller, that means, hey, I have to expand the shade this way, make it longer, right? If your calculated solar profile angle is larger than this angle, that means, hey, I don't need these depths. I can decrease the depths for that application. Okay, makes sense to you? But the real application is very complicated because the sun is moving in the sky, right? So these two angles, front profile angle, side profile angle, is always changing. Okay. This angle will also be different from season to season, different from day to day, even different from side to side. So if you want to find what will be the optimal shade for your building reason, you have to figure out what will be the appropriate range of your profile angles, including the front profile angle and side profile angle. Then you can decide how large your shade should be. So that's actually the design process. When we come to the shading design, we will talk more about that. Yeah, but right now we just concentrate on the calculations. For these two angles, since it's not that complicated, but it's also like a little bit tedious to calculate, I would say you guys can use either like online calculator or you can use my Excel calculator. My Excel calculator actually has everything you need to use. So I will put that as a preference for you, but it's up to you. So let's go back to my Commerce website. So we have the solar position calculations here. So we can just, this is my Excel calculator, right? I showed you last time. So let's do this. This is a few like PDFs for the explanations of those equations. And let's use this non-solar calculator. See what we can find. Okay. Look at this one. So find the sunrise, sunset, solar moon, solar position for any position, any place on the Earth. So we can go to, I mean, this is a default place will be here, right? So let's go down. You actually need to put the latitude, longitude. So I can put right over there, right? Because I have my latitude, longitude on top, which we need all the time. So we can change it. So the latitude is 38.9717, right? And the longitude, if it does not say west, then you should use a negative, okay? Because on the west side, longitude is always negative. In this case, it will be negative 95. Sometimes they don't say negative or positive. They just say longitude number and then followed by a W or E, right? Then it will be the same. 95.2353. Okay. I think that's it. And then you want to define the date, today's date, right? And then what time is right now the time. You used, this is the time zone because we are in daylight saving time. So it's actually only 5 hours difference, but we are actually 6 hours difference if we don't use the daylight saving time. So I think that's it. So let me enter it. You should be see the numbers changed. So right now, the equation of time calculate 5.33. Solar declination like this. Solar noon time is like this one. And the apparent sunrise like this. Sunset. And this is the azimuth. Azimuth angle. Let me see. In degree. This is apparently this is like related to the north, right? So if it's like 109.6 degree in reference to the north side. What will be the angles? I mean, the azimuth angle when we try to convert it to the angle using the reference of the south. Can you do the math? I can actually write down here, so you can. Okay, I will show you at the slide 109.67. So I can just draw it, right? This is the north. This is the source. Because the north counted from 0 to 365, right? So 109, if you do the math, it'll be like this, because this is 90, right? So 109 right here. So this entire angle from here to there will be 109.67. Then what will be this angle? This is what we want to do. Can you do the math? Repeat. Would be 70.33. Right. Right. Because this is the morning time. Okay. So you just did the conversion. And then we should have, let me see, where is my prof angle? So this one does not have the prof angle. Of course, let me see if they have the, they just showed you the azimuth angle and the altitude angle. Altitude angle is 26 degree, right? So let me actually try another online calculator because this one does not show me the prof angle. I should have the prof angle calculated some way. It's this one, solar position calculator. This one might be better or more useful. I mean, they're all useful, but depends on your application. So this one has the day. This one actually can calculate continuously for multiple days. So we don't concern about it like the whole day. We just say, how about just this year, right? 2024. And then let's care about today, September 16th. Let's just do one day, right? Even for one day, it will be a lot because this one calculates every time interval you define. Okay, September 16th. 10 minutes. I mean, it will be too much for us. So let's do 60 every hour. Yeah. And then end the site. So we need to put the numbers here again. 38.9717. And this one should be minus 95.2353. Time zone. I mean, this one should be calculated by itself. Oh, what happened? Right. What happened? Okay. Then let me do, I mean, this one should be time zone 6, not 7. Okay. Surface pressure, we actually don't care much about it. Optional input value, azimuth panel surface, solar constant, interval measurement, shadow band radius. So this one has more than what we need. So we only want an azimuth angle, right? And we also need to have the altitude angle. Where is the altitude angle? Yeah, elevation angle. Sometimes it's called altitude, sometimes it's called elevation angle. It's actually the same. Okay, it's just different terms. Oh yeah, elevation angle. Actually, we don't care about the solar elevation. Just care about the solar elevation angle. And then sunrise time, sunset time, not necessary now. Additional design output value. Our angle. Let me see if they have the prof angle. This one probably does not have the prof angle. Yeah. Right. So let me submit. See what we get. What else should I? Okay. Should I pick one of them here? Let me see. Choose all time. Right. Mean Earth radius equation of time. This is additional, right? So let me just doesn't let me do that. I don't need to. Let me actually just equation of time, just in case. I don't know what happened. Let me see. Yeah, and then 60 minutes. I think it's correct, right? Did I miss anything here? Optional. Check it on. I only have this reset. Did I miss anything? Yeah, 2020, 2020. I think I have everything. Let me just desired azimuth angle, elevation angle, factor, shadow. I have no idea what happened. Let me reload the page. Okay. Maybe something wrong with it. Let me change it back. So do one more time. 16th and the date. Maybe should I specify different date? I don't know. Let me try. Let's say 17th. Should not be on. Let's do hourly. Change this back to the latitude. 1717. Let's change this back to 95.2353. And the others, this should be time zone 6. Remember that because it's not 7 for us. We need the azimuth angle. We need the elevation angle. That's it. We don't need anything else. Oh yeah. I don't know. Maybe ask me to have 2. It's calculating right now. I believe so. Just wait. It's calculating. It just takes. Yeah. Okay, that's why. So you got all the angles here. So you have the date, the time, you have the azimuth angle, you have the altitude angle. That's only 2 we check. So you have from midnight 00. So you see elevation angle, your altitude angle is minus. You see that because it's midnight. So when you see this angle actually positive, it will be 7. So the sign is rising between 6 and 7. Did you see that? Yeah. And then you have all the different values for 2 days. I mean, I should be able to just calculate for a single day, but I don't know why the web page give me some trouble on that. But this way, you will have all the values. Okay. But you don't have the prof angle. Let me try another one. See if we can have the prof angle from the online calculators. Because if not, then we can use our Excel calculator because that's the only one have everything. So another one will be the. Let me see if this is a little bit different. No, we have the calculation, no accuracy equations. You see the low accuracy equations. That means for some calculations, they are approximately, so sometimes you can see differences. So keep that in your mind. So sometimes if it's like 5 or 10% difference, does not mean your calculation is wrong, just mean you used low accuracy equations to approximate. Let's do the latitude, longitude. We don't care about that. We want to see the solar, the sunrise calculator, sun position calculator, solar calculator. Let me actually check the solar position calculator. See, oh yeah, this is actually the one I want to use. Although it's called old, but I think it's very precise. So let me see if we can have Lawrence. I'm sure we don't have Lawrence. The closest one might be Kansas City. Of course, you can always specify the latitude, longitude here, but for me to save some time, I just use Kansas City. And then you have your time on there, assignment time right now is yes. Offset 6, that's your time zone, right? So you have the date, you have your time, calculate it. It's already done. Okay, yeah, it's already done. So you have your solar azimuth angle like this, solar altitude angle like this, and the cosine of solar zenith angle, you don't care about that. So we have the solar azimuth and solar altitude angle. This is a bit different from these angles. Why? Because we just have a few minutes plus. So that's the difference. Okay. Also, we use the Kansas City, right? Not the Lawrence. So do you guys know how to convert the degrees to minutes and seconds? Because this one does not give you all your degrees in digital. It's easy. For example, let's try to convert because I want to show you. 38.9717 degree, right? So you try to convert it to this format. Then the first input should be 30. How about we just do one, right? Do one 38. This should be 38. Okay. And then the minutes, you have in this case, you have 0.9717 degree. How many minutes times 60, right? Can you give me the answer? 58.3. 58.2. What? Did I move? Because we need more digits. Yeah. 58.302. 302. Okay. So this should be minutes. Not, let me actually put minutes here. So this should be minutes because 0.9717 degree equals to 58.302 minutes. In this case, we should put 58 to replace 4, right? 58. And then what will be the seconds? In this case, it will be 0.302 times 60 seconds. Can you do the math? What will be the actual numbers? Should be 18 seconds. 18.12. 18.12. I mean, 0.12. In this case, we just put 18 because 0.12 should be ignored. So we just put, where's my cursor? Okay, 18. Okay, then can you guys convert the longitude? We have 95. So what is the minutes in this case? Mm-hmm. 13? 14. And then what would be the second? 7. Yeah, we got it. Okay. I mean, you can take a photo so in the future you don't have to calculate one more time. Let me take a photo actually. So, yeah. Then you have the answers right here. Finish calculation. 112, 38. For that Lawrence. Okay. I actually prefer to use this. So you can always go to the chapter 2 and then go to that link, pick the old sun position calculator, which actually to me is better than anything else. And then we have more, but I'm not going to show you that. Let me actually show you the Excel calculator because this one is very interesting. I want to show you because none of those online calculators will calculate the solar profile angle for you. You need to use the Excel calculator. That's why my Excel calculator, I think, is more useful in this case. Okay. So this is my online calculator. I mean, Excel calculator. You guys can see the text, right? Is that legible to you? So let me actually put morning time, not afternoon. Oops. Let me move this a little bit apart. Yeah. So let's put AM. Right now we have all the values. Junior day is actually different. Last time you have 2:55. What's the today's day? Junior time. So let me actually go to the junior time. I have my junior time link right here. So let's go to the junior time. This is a leap year, right? So junior time leap year. If you open it, okay, I can open from my actual course collections. Hopefully that'll be easier. So I have my junior time is DPA PDF. Right, open here. Okay. So you have to check the second page because for junior, I mean for the leap year. So we are September 16th, 260. Yeah, 260. Right. So the junior data will be 260. Then let's go back to my Excel calculator. 260. And you don't have to change the white cells because that's the calculated results. On the local standard time, we are concerned about maybe 10, right? If it's like daylight 7 times, then we have to make changes. So in this case, it'll be 9 because you have to adjust it if it's 7 times. And the standard meridian is 90. We talked about that before. Latitude, longitude is the same. So you calculated your solar azimuth 115.5 because we calculated 10 o'clock. And the solar altitude angle is 31. If you convert it to the source, it will be minus 64.5. Okay. So the two highlighted, the yellow will be your answer. Okay. And then your building orientation angle, I just randomly put minus 50. This angle should also be with the polarity, right? So I'm assuming the downstairs entrance lobby for a portion of the windows. If it's minus 50, then your calculated solar profile angle, the inside angle will be 33.9, and your front profile angle will be 31.8, and your side profile angle will be minus 67.4. Let me tell you what does that mean. Minus means on the left side of the window. When you stand inside the window looking out, the sun is in front of you. In the morning time, that's on your left hand, right? So your calculated side profile angle on your left hand will be 67.4. Does not mean it's going down. It means that it's just on this side. Okay. If it's in the afternoon, you should have a positive value. So that's for the morning time. How about if you made a mistake by put a time like in the afternoon? See what will happen. Let's say you want to do 14 hours. I say the input value does not match the data. So you have to check it. That's just the error message. Because if you want to do the afternoon, you have to use this tab, PM. You should not use that morning time, because the calculation equations behind are a little bit deep. Yeah, that's the way I figured out. So I will say my exact calculator will have the most needed functions compared to the online calculators, because online calculators, I don't believe they have the prof angle calculator. So you probably need to figure it out. Go to my modules. This one is stuck right now. So we have basically different types of local to solar time converter, navy, sun, moon, altitude, azimuth, angle tables. Yeah, this one is very popularly used. This one will give you like all the angles using reference to the north. Because for them, for navy, they don't care about the south, they care about the north. So I think that's all the different ways to do the calculation online. Okay. I believe the Excel calculator should be the most convenient for you to use. Then let's talk about the sum pass check. Of course, I will go back to my slide. Okay. So we already talked about them, right? Sum pass check is like this. This is one of the format. It's called the cadencing. But cadencing means you will use the horizontal axis, you will use the vertical axis. In this case, horizontal axis will be your solar azimuth angle, and the vertical axis will be your solar altitude angle. So if you calculate for the whole year, you will get a map like this, a party map like this. If you only calculate for a single moment on a single day, you will get only a point. Make sense? For example, we just calculated a few azimuth angles, altitude angles, then you get a few points on that. So in that case, because today is September, September, October, April, May, June, July, August, September, right here, because they are almost the same line. So September, this is the first half of the year. I did not include the second half, but for September, you should have this line as well. So we just calculated a few points, 9, 10, right over there. Yeah. So if you calculate for the whole year, then you will get this body and line. And this is called the sum pass chart. Why it's called the sum pass chart? Because you see, this is actually the sum pass for the whole year. I mean, for the first half of the year, also for the second half, if you change this to different months. So the sun moves along this line on different days across the whole year. That's why it's called a sum pass chart. Will the sun be moving to this position or be this position for this specific location? What? But if you change to another location, yeah, the sum pass chart will change. So it might be over here, might be over there. It's possible. And we actually have some interesting plots to share with you. So here's the sum pass chart definition. You see the sun moves, right? The sun moves. This is the Earth, the Earth's the surface, right? The ground, and where you're standing right here. So the sun rises from the east, sets on the west, and in wintertime the sun is lower, so you will follow this sun path. And in summer it's higher, it will follow this sun path. So for the whole year, your sun just moves in the shadowed area in the sky. Make sense? If you project the movement of the sun in the sky to an actual path on the paper, you have this shadowed area. And this part is called the polar plot. It's not called the Patterson plot because this is a polar. Let me see. Where is my polar? Because you will have two different ways. This is a Patterson plot, you use the acute angle, If you use the polar, then you use just like this kind of ways. This will actually show the latitude, longitude, like you look at the Earth, right? And then you have the typical month, typical day. So your sun movement will be inside this highlighted area for this specific site. So this part is called the sun path chart in polar coordinate. You can convert it to the Cartesian coordinate, but for us, for building professionals, we typically use this because we think this is more, how to say, like easy to understand and a little bit like intuitive to us, right? So we actually have different projections. You see, we have the orthographic projection, stereographic projection, equidistant projection, equisorial projection. We use equidistance projection for our polar curve. For polar diagram. Why? Because this one will actually give you the most relatable contents without condensed details for some of them, right? For example, if you look at the orthographic, the age of the projection will be kind of condensed. You won't be able to see it clearly. We have too much information. And for the equal distance, you have the equal distance between two angles. So this projection is always preferred for us. Of course, for other purposes, for example, for my camera, age measurement, we always use equal solid. In that case, we do calculations easier. But equal distance, equal solid can be converted. 4 of them can be converted from each one of them. We just use the equation, right? But for us, for the polar sun path chart, we always use equal distance. So this is one example for the equidistance projection for the 40-degree latitude. So you see the sun path chart falling right inside this area. You have very early morning, this is 5 o'clock, 6, 7, 8, 9, 10, to afternoon 6 p.m., 7, 8. We don't have the hours beyond that because the sun already set. So we think it's not necessary. And your chart is always here, okay? And this line is for December. This line is for November, October, September, August, July, June. This is for the second half of the year. The first half will be similar, but with different marks here. Okay. Then let's take a look at the sun path chart for different location. The first one, 90-degree north latitude, right over there. That is exactly the location of Santa Claus, right? Where Santa Claus lives. So for that North Pole, you will have a solar path, sun path chart in polar coordinates like this way. Makes sense? Because you are living right here, your sun will always be moving around you, right? If you are living in North Pole. And if you're living in South Pole, you have similar, but the opposite, okay? Then for 60 north latitude, 60 north latitude might be, say, I don't remember which city will be close to 60, Orlando or Vancouver, might be, right? So for them, they have a sun path chart like this. The limit right here, the sun is always in front of them. This is south, this is north. They will have a chart like that. For 30-degree north, that's a little bit like source of us because we are 38, right? So 30 should be Oklahoma somewhere. So they have a sun path chart like this way. If this is in the equator, you have the 0-degree latitude, you have a sun path chart like this. Make sense? It's a magic. You have half the year sun is on your back and some half the year sun is in front. And then for the 6-degree south, this might be Sydney or somewhere, you have a sun path chart like this. And another degree in the south hemisphere, you have a sun path chart like this. And then going to the south part. So by looking at the sun path chart, you will be able to tell it's different by the location. Okay. All right. Then let's take a look at this one. This one is a SunPath chart program. Oh yeah, how can you do the actual plot? So I will show you how to do it online. This is very important. And I want you guys, where's my cursor? I want you guys to take a look. Yeah, right here. So SunPath chart, I already put a preferred here. So let's click on this one because the University of Oregon, they fix this. So when you click on this one, you have this calculator pop up, create a SunPath chart, right? You will have the options to output. You can do Cadison SunPath chart or Polar SunPath chart. For us, we can use either one, but for convenience, we always use Polar because Polar is more intuitive. You can actually see it. So we can put we can check the Polar right now. We don't do Cadison, or you can do both if you like. Then let's do the input. So you have the latitude, right? So let's do the latitude again. 38.9717. And then you have your longitude, which should be minus, or you can put a west in some calculators. 2353, correct? Right? And the north is azimuth equals to 0, typical for northern hemisphere. So we just use this because for us, we are living in the northern hemisphere. So put the north as your azimuth angle 0. And then your time zone, offset minutes, UTC. This is optional. For us, this should be 6. Okay. We are actually positive because we are on the east side of the Greenwich, right? Time zone, that's 0. And then the Pacific time zone is -8. Oh, okay. So we should use minus 6. I'm sorry. Use -6 because it says Pacific time is -8. Then we are -6. And then this is optional. You don't have to have this to do the plotting. And then specify data range, plot all months, or you can plot a specific day. Do you want to plot all the months for the whole year or just for a single day? If you plot for the whole month, you have like multiple lines. If you plot for a single day, you just have one line. Okay, that's the difference. Right. And then option 3 is plot custom data range. You can plot like the first half year or second half year or from which day to which day you define, right? So this one is actually very useful. But right now, let's just do the typical plot for the whole month, right? Later on, when you do the actual design, you probably find that the option 3 is very useful. Plot tab, we do polar SunPath chart, and then sundial chart, which you don't need. Additional parameters. Minutes resolution default will be 10 minutes. I think it will be fine. If you want to have less data, this is like get you more data. You can do hour data, right? If you need more, you just do more. You pick like every minute, plot contour line, year, month, date, hour, minute. I think it will be fine. And you can also plot the access limit, but I will use the default, right? This, if you don't put anything, it will be default. Image resolution, you can put a beta resolution. Let's say, how about 400? But 200 should be enough for them. Okay. So submit. You're supposed to get something come out. Let me see. We just finished already. Let me see. Let me try one more time because this is also my first time using the. Oh, enter valid value. I think it's valid, right? Latitude 38. North is positive, right? It's positive. I think it's valid. Let me try one time. Maybe ask me to only put 2 digits. Oh yeah. Then let me put 2 digits here. That'll be weird. Let me try. Yeah. Oh yeah, it's coming. So I will tell the writer to allow us to put full digits because this will be interesting. So this one is actually the SunPath chart plotted in SolarPath format. I mean the polar format. So you have we are missing one month. I mean at a certain time. This does not look correct to me. This is not. This is and this should be 12. Something's wrong. Okay. Let me do one more time. So let me go back, double check. No, this one. Let me go back, double check because this is not correct. This is correct, right? Time zone correct. Whole month correct. Polar correct. For the daily contours, yes. For the axis, yes. Let me use a bit less so we can get more data, see if it will change. If this is something wrong, I will let the writer know about this. It's coming. Okay. And this one, download the polar image. Let me download it because it's not very legible. Maybe something related to the pixel resolution. I think I downloaded it already. So let me open it from my download folder. Let me see. This is chapter 2. Again, no, it's right here. It's PNG. It's actually not a PDF, but PNG is also fine. Okay. So this chart has 1 degree, 0, 24. So something is wrong with it. Yeah, something is wrong with it. Let me change to actually another time. If it's wrong, then I will let them know because they made mistakes. They did not correct it correctly. So let me change to a different date, whole month, or just for this option for a single day. 9th, 16. Still want to be okay. Okay. Everything else should be the same. Yeah, still something wrong. Did you see that? Because this is not supposed to be 6 o'clock in the afternoon. This is supposed to be 12. Okay, something wrong with it. I will ask him to correct it, but in the old days, they did everything correctly. Let me show you. But we do have another option over there. But let me show you the actual product they did before. For example, this is plotted from the website before. So in this case, 12 p.m. is right here, right? And this is afternoon, this is the morning time. Yeah. But I will ask him to correct it because they told me last time they did not get any support to do this kind of work. So the person probably asked a graduate student to work on this and oops, something's wrong. Let me actually show you another alternative chart. We do have multiple of them. If that one does not work and you are in a hurry to get the take-home assignment done, you can use this. So we have another alternative SunPath chart. This one is actually very easy. Okay. This is accurate because we tested. You can actually drag it right here. You put in the values. Right now we have, let me drag it. Our latitude is 38, right? Actually, I need to complain about this because this is not very accurate. how can I know I will drag to exactly that point? Okay, close to, right? And then longitude is minus 95 minus 95. That's why I did not ask you guys to use it, because this is not a very precise way. And then day of the year should be September, August, September 16th. This was single day, right? And then time of the day, yeah, I mean, this is for the entire year. So that's exactly the sample check. So what you need to do is just do a swing calc and get it. You actually have the solar time, azimuth angle, angle. That's very convenient. You see, they have everything right here. Yeah. Then I will contact the University of Oregon. Hey, I will tell them, hey guys, sorry, something's wrong, and then you guys can fix it. And if you have another chart, this one is actually similar, but I believe it has a different function over there. Let me see. Alternative 2. This one asks you to put your geographic location. Then make it latitude, longitude. Yeah, you can actually put the values here. That's actually excellent, right? So you can actually put the values here. Or you cannot input. You cannot input, so you still have to do this kind of thing. Drag it, and then longitude minus 95. Oops, it disappeared. Okay, I can drag it back. Data and the time. So it's very similar to that. So you'll get almost the same. So just do the screen cap. So this one is actually the same website, I mean, from the web page, but a different format. So you can use the previous link. But I still hope we can use the Oregon one, because this one actually have very precise way to input everything. But since they did not solve the problem correctly, I will contact them one more time. Last time I contacted them, and then they said they're going to fix it, but not so soon. We're still having problems. Okay, not a problem, right? You still have the alternative option to do. And then for anything else I want to talk about, yeah, because I have something else to talk about. So how many minutes? I think I still have 5 more minutes. So let's talk about them. Right. So right now you already understand the sample chart, right? So this is like cognitive product. Let's talk about the anima. Anima is the sun-path movement of the sun during different months at the same time. For example, this is an anima probably that is seen at noon. You should see this at the same time, but on different day. From the Royal Observatory, Greenwich. So you see, for January, your sun is right. January 1st, your sun is right here at noon. February 1st at noon, your sun is moving to this position. March 1st, your sun moving to this position. So basically, for the year round, your sun position has changed on different day at the same time. Make sense? So this explains to you, for a different sun-path chart like this, you see the anima curve for that specific day. I mean, for that specific time on different day. Make sense? Yeah. And then this slide explains to you the sun position changes across the whole year at exactly the same time. This should be winter. This should be summer. Okay. Why we care about that? Because sometimes we care about the actual location of the sun, then we have to consider about the anima curve. which will be similar. Okay. I think that's all I need to do for today, because shading mask, I want to keep it for next class, right? Because shading mask is actually very complicated, but it's very useful. So I want to talk about the shading mask by taking my time, so you guys can adjust easy. So today we just talk about some chat mostly, and then I will ask you guys to try to use those online products. See if you can find if you some chat for fun. Okay? You don't have to actually print them out. Just it's a screenshot or using that University of Oregon website. See something wrong possibility, but I will ask you to make corrections, because this is just a mark of the time. That's the only mistake. The curve itself looks correct, so the mark is incorrectly. Okay. I will ask you to correct it. Okay, I think that's for today. I will see you guys on Wednesday.